Fuel cell, you do the exact reverse. You start from a fuel like hydrogen, oxygen from the air, and you make the electricity, okay? And in electrolysis, you use the electricity to split the water to make a fuel, okay? And this is in the interest of converting electricity into a fuel. So this is for storage, okay? So the different chapters I'm going to take you through. So a first brief intro. I will insist on the operating principle. I think that's essential that you know how it works. There are different families of fuel cells, depending on the materials that we use, different temperatures of applications, also different fuels that you can use, okay? And so we will discuss about hydrogen, hydrocarbons, okay? Because very often fuel cells are mentioned in connection to hydrogen, and this is true for electric vehicles, okay? Fuel cell vehicles, they have to run on hydrogen, and today you will understand why. And then I'll end up with the reverse operation, which is electrolysis, and this is now known under the new buzz term of power to gas, okay? Which is coming up quite strongly. And you know in which, well, what is the explanation for that? You have, your aim is we want to go 100% renewable, okay? So how can this electrolysis, this power to gas, using electricity to make hydrogen, how can this be useful in the present context of the energy transition? Yes?
Seasonal storage.
Seasonal storage, yes, but even just much more generally, we are seeing a massive increase of wind and solar energy, okay, over the last years. This is really driving the energy transition, and it is intermittent energy, and we have a lot of it. You know, sometimes in the North Sea, when all the windmills are blowing, they have to sell them at negative cost. Okay, they have to really. It's basically not used. Okay, and so there are also plans that you can put nowadays PV. There has been a tender in Saudi Arabia to put up a PV plant of several hundred megawatts. Do you know at what cost the company that won the tender? Do you know at what cost they can produce PV electricity in cents per kilowatt hour? Yes.
1 cent per kilowatt hour.
1.7 cents per kilowatt hour. Okay. So this is how cheap it has become, and it is there. And we have to store this energy, okay? And we can do it, and we can make hydrogen, loads of hydrogen for that. And hydrogen is becoming one of the new vectors of the future that we can use everywhere, and especially in mobility, okay? If you want to decarbonize society, we have to attack all the sectors, and but the sector that is mostly dependent on fossil fuels is mobility, okay? It's almost exclusive fossil fuels, and so this is where we can make a difference. Okay, the short intro. Here you see a picture of a real fuel cell. This is the one that we are making in collaboration with our company. So I run the lab that Francois has mentioned in Sion, in Energy Police. We closely collaborate with industry. And so what they are doing, so this is actually our own startup that we created a long time ago, which is now manufacturing. And so we are making these stacks, we call these stacks of cells like this. Here we see an individual cell, okay? And the idea is that we can inject air and fuel, but as we will see, they are never in contact together, so we are not doing a combustion. We will do an electrochemical reaction. And so there is current. We convert the chemical energy of the fuel directly into current, into DC current. So this particular cell, here we will develop something like 30 amps or so. Okay. And then we have a fraction of a volt, so if we put them in series, we will add up all the voltages. So this particular stack, as we call it, has something like 50 volts. You multiply the volts with the amps and you get the watts, 1.5 kilowatt. Where can you use this? Typically in a house, okay? This would be this is a cogeneration unit that you can put in your house if you are connected to the gas grid, national gas grid, which is the case for 37% of households in Europe, okay? So it's more than 100 million households, okay, that are connected to the gas grid. The idea is that you convert cleanly this fuel without emissions, without polluting emissions, because we don't have a combustion process, and very efficiently at this low power scale. Okay, so we reach more than 50, in fact more than 60% efficiency, net efficiency on this power level from natural gas to electric. And this is you can't do that with any other technology at this scale. Okay, yes.
Do we always have that much of heat production fuel cell, or is this system made for producing oil?
Well, it depends. So sometimes it's for power generation only, but more usefully it is for cogeneration, because you can actually recover the heat. And for a house, this is typically what you would do. Okay, that you recover also the heat to make hot water in this case.
But if you have a fuel cell in a car, you will also produce waste heat.
Yes, that is a very good point, and this is indeed. But what do you do with your gasoline and your diesel? How much of the energy of your gasoline and diesel goes to the wheels? Do you know that?
20%.
Yeah, 15 to 20%. Okay, so with a fuel cell, you are doing it for 50%. Okay. So you have a factor of 2 to 3 better. Okay. Moreover, you're doing it with hydrogen as a fuel, which means no pollution. Right. So you are A, much more efficient. B, you are much cleaner. And it's the cleanliness that for the moment is driving the interest to fuel cells. Asia is massively looking into this. China has basically a pollution to clean its cities, okay, to clean the air. And this touches everybody. It's not only the poor people, it's all the rich people as well. Everybody is concerned. They are massively moving towards hydrogen and to fuel cells for this reason, yes?
What real efficiency do you have here? Because the thing is, yes, you have a better efficiency from tank to wheel,
Yeah.
but the well to tank,
Yes.
how does it work so far?
Yes. You have to make the hydrogen, and this is obviously a penalty, but as we will see, the overall chain, you remain more efficient. You remain more efficient anyway, but especially is that you are pollutant free, and you can be completely renewable, okay? Because we make the hydrogen from renewable electricity. So the best term I can find the equivalent term to a fuel cell is a gas battery. Okay, just think of it as a battery that you fuel with gas and with air, which continuously converts it into electricity. Okay, and so we can go from only a few watts, so where you can use them, where you can actually replace batteries, standard batteries, okay, to kilowatts for houses, to tens of kilowatts for cars, to hundreds of kilowatts for buses. Okay. And then to megawatts for, let's say, stationary cogeneration, decentralized cogeneration, also using renewable fuels like biogas, for example. Okay. So the key is the direct conversion of the fuel to electricity, which gives it its high efficiency. So the fuel is the oxidizer substance that's basically an electron donor. Okay, and the electron acceptor will be the oxygen from the air, right? So we are doing an exchange of electrons between oxygen from the air and the fuel, but we are not doing a direct combustion. Okay, we are doing this via a separate electrochemical reaction, as we will see, and this is how we convert the chemical energy of the fuel into electrical energy and heat. So the loss, as your colleague asked before, the loss is always heat. So this is the case that obviously in a car, the heat that you don't use, it is wasted to the environment, or you use it in the cabin, okay? And this is important if you go to large vehicles, for example, to buses and trucks, you recover a part of the heat of your engine or your fuel cell, also for cabin heating purposes. So fuel cells, this is a log scale of the size of the system. So this is kilowatt, megawatt, gigawatt. Okay? These are electrical efficiencies, LHV, so lower heating value based on natural gas. And so you see, you have the traditional combustion technologies, turbines, engines, and so forth, which are more or less in the 20 to 30 to 40%. And only for the very large power can you go to 50 and 60%. Okay? Fuel cells have their strength that already, because of the different operating principle, because we are doing electrochemical oxidation and not the combustion of the fuel, we are much more efficient for small power. Okay? And as you see, there are different fuel cell types which we will discuss. So operating principle. Let me first start with a battery. Okay? The classical lead-acid battery that probably you're all familiar with, at least by name or what it does. Okay, is the one that you have in your car, which is a starter battery. Okay, which consists of lead and lead oxide, and in between is a liquid. It is sulfuric acid. Okay, don't be misled by this drawing, which for drawing purposes is shown not at all on scale. In reality, we want the distance between the two electrodes, because this in fact are two electrodes. Okay, this will be the plus and minus of your battery. Okay, we always want to keep this distance very, very short in order to limit the losses. Okay, because there is current going through the system, and the thicker you make distances, basically the bigger you make ohmic drop. Okay, it's you increase the internal resistance of the system. So what actually happens? We have lead metal and we have lead oxide. The lead metal will want to give electrons, okay, to the lead oxide that want to take them up, and both will actually make lead 2+. Okay, so here we oxidize the lead metal, here we reduce the lead oxide to lead sulfate. Okay, so to Pb2+, right? So we have an exchange of two electrons. So the lead and the lead oxide are not in direct contact. Okay. We need an ionically conducting medium in between, and the electrons, they do the outer circuit, okay? And if we measure this at rest, if we go with our voltmeter and we take our battery, how much do we measure? The car battery? What is a car battery? What voltage is it? It's 12 volts. So I say here 2, so that means you have 6 elements in series. Okay? You just add up the voltages and the same current goes through the system. This is at rest. Okay, so you don't draw any current from the system. If you draw the current, then you will get a voltage current characteristic. Okay, so you can pull current from the system, and your useful voltage drop between plus and minus is basically going to go down because of the internal resistance. Okay, because we have losses happening at the interfaces and losses within the connecting leads and so forth. Okay. The essential point is of a battery, of a classical battery, whether it is primary, so it means you just use it until it's empty, and then you have to replace it, or the secondary battery, which is one that you can recharge. Okay? So where the reaction goes both ways. Right? If we recharge our battery, we are basically decomposing back lead sulfate to lead and lead oxide. Okay? And this you can do for a number of cycles until you have to rechange your battery. Okay? So the essential thing about a classical battery is that the energy, the species that participate in the reaction, they are stored in the electrodes themselves. Okay? We are consuming lead and lead oxide. Okay? And this is very different from a fuel cell, where these will become simple catalysts, and the active species that we're going to convert will be the fuel and the oxygen of the air that we inject. Okay? So if I come now to a first type of fuel cell, and taking some similarities with this lead acid battery, so you see, and now I have platinum, no longer lead, and I also have an acid here. It's not sulfuric, it's phosphoric acid. But this is a first of the several fuel cell types that we will discuss. But this is the so-called phosphoric acid fuel cell. The name of the fuel cell always refers to the central part. In this case, the electrolyte. Okay, we call that the electrolyte. An ionic conductor. It's conductive for protons. Okay, an acid. I think you're probably familiar with that much chemistry. You know, an acid is typically it's a proton conducting medium. Okay, so we will feed now with gaseous hydrogen. That actually is going to split. I'm sorry about this. This is a mistake. Of course, it's 1+. That's going to split in hydrogen ions, so protons and electrons. Okay, it's going to do that by absorbing on platinum particles, okay, splitting, and then just giving away an electron to the platinum. And on the other side, I'm going to feed with air, or with pure oxygen, typically it's air. And so it's the oxygen of the air that is going to sense, even though they are not in physical contact, but that across my two electrodes, that is going to sense the presence of the hydrogen on the other side, okay? And there will be a natural trend. Always, if you put in contact two different materials, no matter which ones, one will always rather give away electrons, whereas the other one will rather take them, okay? And there will be a difference in potential created between the two, and this is governed by thermodynamics, as we will see, okay? So here, it's not 2 volts, like with lead oxide, where there is a bigger, let's say a bigger drop, a bigger gradient of electrons that want to go from the lead to the lead oxide. Here, the drive for hydrogen to give away its electrons to oxygen is at rest, at room temperature, is about 1.2 volts. Okay. Here, this fuel cell is a little bit warm. Okay, so this is why it's it's a little bit lower the open circuit voltage. Okay. So again, this is at rest. If we now put a load to the system, then we can develop current. Okay. And again, we will have a voltage current characteristic, with the voltage going down, the more current we draw. And what happens physically? Okay. What happens is that my protons that I have made here, they will go through this central membrane to this film of liquid, it's a thin film of liquid, and react at the other side with oxygen, with the electrons, okay, to make the product, which is water. Okay. We have an electrochemical oxidation of hydrogen and oxygen to form the product, which is water. Okay. So the difference with the battery is that my electrodes, they are not consumed. Okay. They are not regenerated. They're just there, sitting as catalysts, doing the job of taking away electrons from hydrogen and giving them to oxygen, and absorbing hydrogen molecules, absorbing and splitting oxygen molecules. Okay. They are catalysts. We will come to it why it has to be platinum, okay, and why it also is hydrogen in this particular case. So the consumption is, the generation of electricity comes from the fuel and the oxygen. Okay, so as long as you feed the system with those flows, you basically run your gas battery without end. It's a battery that is inefficient, okay, so that you can't exhaust as long as you feed it with fuel. So this particular system runs at around 200 degrees. For special reason, this is to maximize the conductivity of your phosphoric acid. Yes?
So the water is going away as steam?
The water is going away as steam in this case, yes, because we are above 100 degrees. So here we generate it as steam, indeed, yes. So you see we have ambient temperature fuel cells where we will produce liquid water, and we have higher temperature fuel cells where we produce steam. Okay? And CO2 if we run them on hydrocarbons, which also is the case. So you see that this is a cogeneration system, okay? We produce electricity and heat. Right? Just to fix order of magnitude, on a square centimeter of active area, we have a few hundred milliamps. As I said, this particular fuel cell, we pull a few 10 amps through this. So then, of course, if you want to go to, let's say, sizable systems, which is what you do with this fuel cell. Here, this type of fuel cell, you will make electrodes a square meter, okay? Or not quite. It's about the size of this block here, okay? And also about the same height. So imagine that this would be a phosphoric acid fuel cell, okay? That could produce at least 1,000 or 2,000 amps easily, okay? And then maybe 100 volts or so. So you would be making a 200 kilowatt system, and this is exactly how it is done. So we then put these individual cells in series, and we need in between each couple, between each plus and minus, we need a so-called bipolar plate or interconnect plate, because the plus of one cell is in series with the minus of the next one. Okay, but the plus is fed with air, whereas the minus is fed with fuel. So you need a gas separator, okay? But at the same time, that gives an electrical contact, right? So the easy way to do it is to have a plate here that has channels machined in it, okay? So then the top make the electrical contact, and the channels allow for the gas to circulate and to extract the product. Here in our type of fuel cells, this is a bipolar plate. So this is a metal plate. As you see, this is a ceramic, okay? We work with ceramic fuel cells, I will come to that. And this is the bipolar plate, which is a metal. Obviously, we have a trick, so we don't machine this thing, because then it would be thick and heavy and it's expensive. So we have other tricks that we make the electrical contact and that we have the gas, that we allow for the gas to circulate. So imagine then that you have hundreds of these cells in series, and then for thousands of amps, which you can produce, and this is how you can make systems of hundreds of kilowatts, okay? And this is what's been done for this particular fuel cell, okay? So you can buy them in a box, in a turnkey system, which is nowadays 400 kilowatts, okay? Operating on natural gas. So what you do is you convert your natural gas into hydrogen, and then the hydrogen into electricity and heat. So this is a cogenerator. This is around 40–45% efficient. So you produce from a megawatt input of natural gas, you produce 400 kilowatt electric and 400 kilowatt heat. Okay, and this particular box here was standing on the playground of a school. Okay, where kids are playing around. So it's a very safe system, non-polluting whatsoever. This is then 5 those blocks, which would be 1 to 2 megawatt. This is out in Alaska, so you can use them also in let's say in cold environments. Yes.
I was just wondering, when you're saying non-polluting,
yes.
What happens to the CO2 when you have?
Well, CO2 is not a pollutant. CO2 is a product of combustion. But of course, you are right. We also have to deal with it. So if you start from natural gas, well, your CO2 is going to be a product, okay? And then you have to decide what to do with it, or whether you, in our case, what we are proposing to do is to re-electrolyze it to methane, okay? Which is what we also do with our fuel cells, as I will explain. So our systems are perfectly reversible, so we can convert methane into steam and CO2, and we can electrolyze steam and CO2 back to methane. Okay. So, but eventually, of course, the CO2 issue is one, and we have to do something about it, and we have to somehow find a solution, first of all, to produce much less, which is what we do, and then also probably to take it out of the atmosphere by, the simplest thing would be really to split it and to make carbon, and basically just to store it back as carbon. Okay? If we want to be really drastic about it and get rid of large amounts, or biologically, or carbonization. I think maybe you have a lecture about the CO2 issue with François. So okay, I'll skip this. This is you can look at. I just want to move to the second type of fuel cell, which is a polymer electrolyte. So again, as the name implies, here is the key component is a polymer. Okay, so it's a polymer. It's a really the best way I can explain it is it's a plastic film. Okay, it's a plastic film of very thin, 50 microns, 100 microns, that has a special structure, and that has to be kept humidified. Okay. And in those conditions, it is capable also of conducting protons. Okay, so you see, this is the polymer backbone. So this is a carbon chain, entirely fluorinated, which gives it a very stable structure. It's actually very similar. The structure, this membrane is called Nafion, and is quite similar to Teflon. Okay, I think you are probably familiar with Teflon. It's a very stable polymer. So here is the same, only that you have side groups which are sulfonic. So we are somewhat like, it's an acidic polymer that is capable of conducting protons. Okay. Again, we use platinum as the catalyst. So you have to imagine that this platinum here, it's nanoparticles that are suspended on carbon paper, okay, porous carbon paper, which is there as a support and which is also there for conductivity. Okay. And again, the same principle. We feed with hydrogen on the one side, oxygen on the other side. We develop an open circuit voltage at rest. And when we make a fuel cell run, it means we are consuming hydrogen. Our protons go from the fuel side to the air side. We make water here. And we have a certain characteristic. And so this is the fuel cell that is used in cars and in buses, okay, for mobility. Because this is a fuel cell that you can cold start. Okay? You can even freeze start from minus 20. Okay? So you can, and then once your fuel cell gets going, it heats up because of the electrochemical reaction. It is very efficient. It converts 50% of the energy of the hydrogen and electricity. The other 50% is heat. And some of the heat is just basically used to maintain the fuel cell, and the rest then to heat the cabin and so forth. Okay. So this is where all these companies, Toyota, Hyundai, actually almost any car manufacturer in the world is having some kind of a fuel cell program. Okay. And some are already on the market, like Toyota, like Hyundai, like Honda, and a few others. So you can buy fuel cell cars now. So this is a closer look on the structure. Okay, so this is the polymer backbone, this is the side view, and here you see how we can actually conduct electricity in the form of protons in a plastic. Okay? And then you see, as I mentioned, so then this plastic film is sandwiched in between two carbon papers, okay, that are loaded with platinum particles. And then you need bipolar plates. You need plates with channels so that we can inject hydrogen, inject air, and extract water. Okay, and then you basically stack them together, and you make these pretty compact systems. In the case of Toyota, they are now producing a 3 to 4 kilowatts per liter of stack. Okay? So they make 100 kilowatt fuel cell. So it's about a 30 liter engine, if you want. Okay, but it's in fact a fuel cell stack developing 100 kilowatt of electrical propulsion power. Here again some examples. Here you see these plastic films and this carbon paper, and it's very lightweight. It's very lightweight for mobile application. You like to avoid steel if possible, so we use graphite, okay, or composite plates, conductive composites, mixtures of graphite with polymers. And you see different applications. So few watts to power electronics. Camcorders, computers, phones, and then 2 kilowatts for houses, to tens of kilowatts for cars, and so forth. Okay, hundreds of kilowatts for buses. So now an important comment, because you say, okay, well, hydrogen and platinum. Okay, well, why? So we have seen those first two types of fuel cells, and we will see more. So these two types, we see that they conduct protons, right? We have a plastic film, or we have a liquid, an acid, that is capable of conducting protons. So they operate at 200 or at ambient temperature, and this is the explanation. This for catalysis, for electrocatalysis, this is low temperature, okay, especially ambient. And so the only way to get a reasonable performance, okay, to develop a reasonable current out of this, is that you need a very active fuel, and you need a very good catalyst to do it. And nature has decided that the best fuel is hydrogen, because it's very small, it's very reactive. We just have to split. Okay, it's a single bond. Okay, and the catalysts that are very good at doing this is the noble metal group. Okay, it's platinum and its brothers. Ruthenium and iridium and these very expensive ones. Okay? So that's bad luck, but it works. Okay? And after all, they are not amongst the rarest elements. There are others that are rarer. In fact, lead is quite a rare element. And if we talk about other alternatives in mobility. There's a lot of talk about lithium, right? Lithium, which is a classical battery material, also due to its light weight, well, it's also quite limited. Huh? If we want to populate all the cars, if we want to run them electrically, like Elon Musk from Tesla would like to do, I mean, he's going to run out of lithium in a split of a second. Okay, so we also have to consider that. Platinum is already used. The noble metal, they are already used on a wide scale in automotive. Okay, for example, the exhaust treatment catalyst. Okay, the three-way catalysts that you probably know. Okay, that deal with the exhaust. They contain platinum and they contain palladium. Okay, so have to be recycled. So that's the explanation. Okay, why platinum and why hydrogen? Okay. And this is also an explanation why we need a hydrogen infrastructure if we want to develop fuel cell mobility. Okay. I will come back to that. So now the next fuel cells that I'm going to discuss, they have a form of oxygen conductivity. Okay, the first two is proton conductivity, it's from hydrogen. The others, the remaining ones that we're going to discuss, they involve a transfer of charge of an oxygen species, which will go from the air side to the fuel side. Okay? So two of them, they run at high temperature. One uses a molten salt and the other one uses a ceramic. The ceramic is the one I brought with me. Okay? So they run above 600 degrees. Okay? And they conduct oxygen. Now you may say, oh, okay, well, this temperature, we're going to have to get these systems hot and all that. Yes, you have to start them up, you have to get them going. But once they go, they open up advantages that we are no longer limited to hydrogen. Okay? So now we can start using hydrocarbon fuels because things are always accelerated and are easier to do at high temperature. The catalysis, the electrocatalysis, the conduction becomes much better. Okay? Point one. Point two, we no longer need noble metals to do the job. Okay? At 600-700 degrees, we can use alternatives, cheaper alternatives. Nickel is a very good catalyst. Okay, and certain oxides and so forth. Okay, so you see the pro and con of the two. Huh? So in the cold, you can start immediately, but you have to rely on platinum and hydrogen. Okay? If you are, and it's for mobile application. If you are more in a stationary application and where you have to pretty much run in steady state or you have to rarely cool down your system, then it makes sense to have a high temperature fuel cell. Okay, use a hydrocarbon fuel like natural gas. Okay, and then do with cheaper catalysts, right? So this is the big difference. Okay, there is one other case. Which is an alkaline fuel cell, which is also a low temperature fuel cell, okay? Which, as its name implies, uses an alkaline medium as the conductor. So it's potassium hydroxide, which is an extremely cheap chemical, okay? And which is very conductive for hydroxide ions, okay? And you may think that it is pretty much the same as what we've seen before, as a phosphoric acid fuel cell or the polymer fuel cell. Well, overall, yes, of course it's the same, that we still feed with hydrogen on one side, with oxygen on the air on the other side, and we make water. But for those of you who paid attention, the fact that, it's no longer protons going from left to right, but it's hydroxide ions going from right to left. This changes the electrochemistry, okay? And in an alkaline medium, things are easier to do, and we can use alternatives to noble metals, okay? So, still, we would get the best performance if we would use platinum in this case, okay? Because we are at low temperature. But we can use alternatives and do rather well with that, okay? Just as like nickel and silver, for example, which are considerably less expensive than platinum, okay? So the electrochemistry is different, and we can make fuel cells with this combination. Also, there is a development also to put those in cars. There is a development to put those in stationary systems to recover hydrogen from as a byproduct. For example, do you know an example case where hydrogen is made as a byproduct? for example, salt electrolysis. Salt electrolysis is something which is done on a very large scale. Okay, you start with salt, sea salt, table salt. Okay, and this is your starting ingredient to produce what? So it's sodium chloride. So the interest is to make chlorine. Okay, interest is to make chlorine and to make sodium hydroxide, which are two very large volume chemicals that are produced on a worldwide basis. The co-product in this electrolysis is hydrogen, and most of the time it's just vented to the atmosphere. Okay, just wasted time. So one way is at least to recover that because it's substantial amount. It's also been, the alkaline fuel cell was the one that has traditionally been developed back in the 60s, 70s to put on space missions, okay? The NASA space missions, Apollo, Gemini, they had typically a small fuel cell on board, which was of the alkaline type, to generate just the couple of kilowatt electric that you need on board, okay? If you have seen the film, the movie Apollo 13, with Tom Hanks, so there's quite a lot of talk about fuel cells in that movie. Okay, the fourth one, the solid oxide, and this is the subject of our research. Okay, so my research group is mainly working on this solid oxide, the fuel cell. So as you can see, we are now leaving the low temperature and the liquids. Okay, we no longer have a wet polymer, we no longer have a liquid acid or a liquid alkaline solution. We are now with a completely solid system, a ceramic system, okay, where we have a ceramic that is capable of conducting straight away oxygen ions. Okay, so principle is always the same. Now we just simply conduct. We just charge the oxygen from the air with electrons, becomes an ion, and it can go through these structures. It's a membrane. It's a very, very thin ceramic membrane. You can hardly guess it here because you see one side, which is the green side, which in fact is nickel. Well, it's nickel oxide, but it becomes nickel during operation. Here, this is our fuel catalyst. The other side, the black layer, this would be this catalyst here. Okay, it looks exotic, but in fact it isn't, because manganese and strontium are extremely cheap, and lanthanum is, well, it's a rare earth, but a rare earth, much less rare than many other elements. And so this is an oxygen reduction catalyst, which is very stable at high temperature in oxidizing atmosphere. Okay, it would be a bit tricky here to put the metal, to put the cheap metal like copper or iron or whatever, because we are at high temperature here in oxidizing environment. High temperature, why? Because in order to make these ions move in this solid structure, we need the high temperature. Okay, at room temperature, this thing is an insulator. Okay, I cannot pull any current through. But once I heat it to 600-700 degrees, my very thin membrane, which is in between my two catalysts, becomes very conductive. And then I can pull amps through this system. It's because the oxygen has to jump from a lattice side to lattice side in order to pass on the current. And so now, since we are at high temperature, we are no longer limited to hydrogen fuel. Okay? And we can start using other fuels such as carbon monoxide, such as methane, such as methanol, okay? So hydrocarbons. So this is now, it opens up the choice of fuels that we can use with this high temperature fuel cell. Okay? And you see, depending on the fuel, we need 2 or 4 or 6 or more electrons. Okay? The methane, for example, oxidizing the carbon to CO2 and the hydrogen to H2O, we need 8 electrons. Okay? Okay, here's some examples. So, well, you have seen already the example of how we stack this thing. Many companies are doing that in Japan for, you see, for kilowatts, and this is something that you put in your basement, right? You connect to the gas grid, and you make your own electricity from gas, okay, and heat. Then you can also make tubular systems, okay, as you can imagine, since now it's solid, so there is no limitation to the shape. All the other fuel cells so far we have seen is basically plates that we stack on top of each other. It's to make the current path very short. But in ceramics, you can make very robust tubes. Okay, they run very well. They have done their service. it basically turned out that it's pretty expensive to make. Okay, and so now the planar type is still more of interest, but it has been demonstrated to be very robust and long living. Rolls-Royce Power, which is maybe not immediately a fuel cell company that you would think of, but Rolls-Royce has been developing this for decades now. Yeah, in other cases here you see the classical stack. Okay, and then maybe just the last one, and then we'll do a break. So then I just introduced the last type of the 5 fuel cells. Okay, and this is where we use this molten salt. Okay, as the conducting medium. So we have seen a polymer film conducting protons, liquid acid conducting protons, liquid alkaline solution conducting hydroxide ions, a ceramic, an all solid conducting oxygen ions. Okay, this is now yet another case, and this is the last one, I promise. So this is a so-called molten salt. It's potassium carbonate, which is again extremely cheap. Okay, and if you bring that to the melt, above its fusion point, it becomes highly conductive for carbonate ions. Okay. So now this complicates our whole system a little bit, because before we just had always oxygen as a feed, okay, air. Here we need, since we have to make the conducting species here, we have to co-feed with the air, we also have to co-feed CO2, okay? Which can make it interesting, also, you know, to put it at the exhaust of a power plant, because then actually you can use the CO2 in order to drive this type of fuel cell. Okay? You mix it with air properly, and so basically you still have, so it's like the oxygen is sticking on the vehicle molecule of CO2, okay, being conducted from one side to the next, and on the other side it is released again. Okay. So what you do in reality is, in fact, and again it's high temperature, so you can use different fuels. In reality, what you do is that this CO2, which has basically been transferred to the membrane, which you need at the input here, and which you release at the outlet, that you recirculate that. Okay. So this makes this type of fuel cell quite a bit more complex to manage than the other ones we've seen, where we simply go in with fuel and air and we extract water, let's say. Here, we have to, in addition, we have to handle this CO2, right? So this adds some complexity to this system, and this is the explanation why you don't find this fuel cell in as small units, okay? Because it would be totally unpractical and uneconomical to make watts or kilowatts with this system. So this fuel cell is made in megawatt size, okay? And so you see these are some examples here, like up and running at different sites. So the smallest ones that you can find are a couple of 100 kilowatts, and then they go to megawatts. And in fact, the largest fuel cell in the world, which is up and running in South Korea, is a 60 megawatt fuel cell, and it's based on this technology. It's 20 modules of 3 megawatts, okay? And this is powering the small town, right, more or less. Okay, so I suggest we have a break here. That's what we usually do, right? And then we start again in 15 minutes. So we have seen now the 5 types, the 5 architectures, the 5 families of fuel cells that are around, that are being made. So here you have another overview of them. So remember just that we distinguish them by name. It points to the electrolyte, okay, to the central membrane, the ionic conductor. Just here, with the polymer electrolyte, an alternative name, if you run them on methanol, they are called DMFC, direct methanol. So I did say that we have to use hydrogen at low temperature. We can use an alternative fuel like methanol. The difference is that because it's so much less active, we just have much less power output. Okay. So for the same device, if with hydrogen you would get 100 watts, with methanol you would get maybe 10 or 20 watts for the same cost. Nonetheless, it may be of interest, typically for small power application, because methanol is a liquid fuel which is easy to store and it has a high density. So with one cartridge of methanol, you can power a device for a long time. Okay. And so you see that they are, what is characteristic is the operating temperature. So we go from low temperature to intermediate to high. Okay. And this is then connected to the fact that at low temperature we have to use hydrogen. Okay. And at high temperature we can use hydrocarbons. Okay, and then these are the different materials that are involved. I don't want to dwell on this, so just remember that low temperature is typically platinum, with the exception of alkaline, where we can use alternatives to platinum, and high temperature is nickel. Okay. Right, now something about efficiency. Okay, why are these things so efficient? Well, we have to look a little bit into the thermodynamics, and I'll say something about Nernst voltage, Nernst equation without having the time to actually derive it. So you'll just, but I can't say something about fuel cells or electrochemistry without saying something about the Nernst equation and about the Butler-Volmer equation, because that's really central in the whole of electrochemistry. So, but the thing is that just the basic notion is that this equilibrium voltage that we have seen, you know, this 1 volt, 1.1, 1.2, for the hydrogen-oxygen case, this is governed by thermodynamics, okay? It directly follows from the Gibbs free enthalpy that you can get from the reaction, hydrogen plus oxygen, okay? And then we have, as we develop current, as we draw current from the system, we just have a number of losses, okay? Just have a number of losses that cause us this equilibrium voltage to drop. We have ionic losses, conducting losses, ohmic ones, and we have non-ohmic ones, okay? Ohmic ones are just linear with current, so this is just simply due to conduction through the medium. And then we have at the interfaces, we have transfer of charge and of mass, and there we have non-ohmic relationship, and so we talk about the polarization of our electrodes, and this also translates to voltage losses, okay? And of course we want to minimize that. Right, so basically the input in the system, you know, in thermodynamics you always put a box around your system and you see what goes in and what goes out in order to compute the efficiency. What goes in is my chemical energy. Okay? So this is the total heat of reaction. Right? And then usually there's only a part of that I can transform into work. Okay? And this is the Gibbs free enthalpy. Okay? Gibbs free enthalpy corresponds to the maximum work that I can get from the total heat of my reaction. Okay? Now, for hydrogen, for example, there is a loss factor. And what is the difference between the two? Which is the thermodynamic function that expresses the difference between the total enthalpy and the free enthalpy? Entropy. Entropy times temperature. Okay. Entropy is irreversible, it's unavoidable heat loss. Okay. In a transformation. Now, with hydrogen, this ratio of free over total will be less than 1. We have a loss, we have an entropy loss. With a fuel like methane, okay, which is the main constituent of natural gas, the entropy change is close to 0, which basically means that all the enthalpy of my methane, of my natural gas, is free enthalpy, okay, which makes it intrinsically more efficient than hydrogen. That's another example, it's another advantage of using natural gas as a fuel. Okay? So this free enthalpy is directly related to the open circuit voltage, which we call the Nernst voltage. Okay? And then this is in equilibrium, so this is the highest voltage you can get, you're not drawing any current, and then as soon as you start to draw current and you use your system as a power generator, then we have these losses that add up and that make the voltage go down, and this is eventually how we have to express an efficiency when you are at this stage, output with respect to the input, okay? And we will come to that. So, do you know this electrochemical series of the elements? You know, somebody knows it? Has heard about it? Yes. Okay. So basically, it's as I said. Okay. So in nature you can take any two elements, okay, different elements, and put them into contact with each other. One of them will give away electrons, the other one will take them up. Okay, and And the willingness or the driving force with which they are doing that, it's expressed by the voltage difference. Okay? And this voltage difference comes directly from thermodynamics, okay? From the Gibbs free enthalpy of the reaction between those two compounds. So you can always measure any voltage difference between any two different elements or compounds, okay? So you have to put them on a scale, and it has been decided that somewhere we put a 0 on the scale, and the 0 happens to be hydrogen-proton couple, okay? So anything left from that is negative. So anything that gives electrons to protons to become hydrogen is to the left, and everything that is to the right, that is positive, it will oxidize hydrogen, okay? It will take electrons from hydrogen. And so on this scale, for example, oxygen will be on 1.23 volts, that's at room temperature. That's the zero potential, the rest potential that you can measure between hydrogen and oxygen at 25 degrees, 1 atmosphere pressure. Okay. This is how we see, for example, also how we reach those 2 volts for the lead acid battery, because my lead metal is minus 0.36 and my lead oxide is plus 1.68 on this scale. So the difference between them is 2 volts. Okay. You also see that lithium, for example, is all the way to the left. There is nothing to the left of lithium. It's the most electronegative element, minus 3 volts, which is one of the reasons why it is used in batteries, and especially for mobility, because it is so electronegative. Okay, with only one couple you can get a high voltage. The other reason being that it is so. What is the other reason why lithium is a very good battery material? If you think about mobility, about transport. Because it's so light, huh? Because it's the third element after hydrogen and helium, okay. Very low density, which is of course of interest in the case of mobility. Okay, so a hydrogen-oxygen fuel cell creates at standard conditions 1.23 volts. Where is this coming from? Well, take the Gibbs free enthalpy of this reaction at 25 degrees. It's 237 kilojoules per mole. Okay. And so you have to convert, what you do is you convert this energy, these joules, into volts by looking at how much charge is exchanged, okay? Because volts times charge, Coulomb, gives you joules, okay? So basically, what my hydrogen does here, it gives 2 moles of electrons to oxygen, okay? 2 because it's 2, okay? Because 1 hydrogen is giving 1 electron, so 2 hydrogen are giving 2 electrons. This is what the little n is for, okay? The n is actually for 2. How many electrons are transferred in one reaction? And how much charge do I have in 1 mole of electrons? It's the Faraday constant, okay? You know the charge of an electron, okay? Which is 1.6 10 to the minus 19 Coulomb, right? And you know how many electrons I have in 1 mole? It's Avogadro's number, right? It's 6 times 10 to the power of 23. This is per mole. So I multiply these two, okay? And I have the charge in 1 mole of electrons, right? And if I do that, I find 96,500 coulombs per mole. This is Faraday's constant. So you take the free enthalpy of the reaction, okay, delta G, you divide by Faraday's constant and the number of electrons exchanged for one reaction, in this case 2, and that's it. You have your rest voltage. Okay. Yeah, I'll skip this in the interest of time because otherwise it's going to take me too long. Just know that you can set up. This is the Nernst equation. So this is the voltage for an oxygen conductor, and this is for a proton conductor. You have this. This is the standard voltage. That is when all the components are at standard in the standard concentration. It means it's 1 atmosphere for pressure. It's 1 liter per mole for liquids and so forth. So obviously you can imagine that there will be an effect of partial pressure and of total pressure. Okay, so If you operate your fuel cell under pressure, if you operate it with air instead of oxygen, air is 21% of oxygen, okay? If you operate it with dilute hydrogen, it's going to affect the voltage. And the way how it affects it is described over the equilibrium constant, okay? And it goes into this term here. But you can forget about that, this is just for... If you want to go more deeper into it, you can't avoid to talk about the Nernst equation, okay? So this is basically expressing the voltage of your system, taking into account also concentration and pressure, okay? Not just time conditions. Right. Okay, I'm also going to go quick here. So we have one type of loss is conduction. Okay, it's ohmic loss. Very simple. You have an electrolyte. It has a certain thickness. It has a certain section. It has a certain conductivity. The conductivity is the intrinsic materials property. Okay, the conductivity is the inverse of resistivity, and conductivity is expressed by concentration of charge carriers times the mobility. Which is one reason why it is good to use things like protons or hydroxide ions or lithium ions, because these things are very mobile. They're very small and they're very mobile, and therefore high conductivity. Okay? So the main ohmic loss is in the middle membrane. Okay? It's simple resistance. Okay? So you want to put 1 amp through, or 2 amps or 3 amps. It's basically your voltage will multiply with the internal resistance of this component. Okay, so I think I'm going to skip this again. Just know that ionic conduction is not at all like electronic conduction. Okay, so a metal conducts very well, right? The metal has micro ohms of resistance. An ionic conductor, you rather talk about an ohm resistance. Okay, 1 million times higher resistance. Which is the reason why we try to make these things really thin, okay? This is why we make micron thin or 100 micron thin plates and membranes, so that we get fractions of ohms resistance, and therefore we can pull a lot of current through. Okay. And then we have ohmic losses, and then we have non-ohmic losses, so-called polarization losses. Where are these coming from? I think it's best to explain this with an example. I think you can understand the physics behind it, or the whole physical chemistry. If we have hydrogen, okay, going to proton and electrons, what happens in detail, step by step, is that my hydrogen has to somehow diffuse through the structure, has to go and absorb on platinum particles, has to split, okay, into atoms, and then give away an electron. Okay, so all these steps, they can be limiting. And one of them is this is the limiting one. It can be the charge transfer, or it can be the mass transfer. Okay, and this is associated to a voltage loss, which is non-linear with current. Okay, you may have a certain. In fact, for charge transfer, you have a kind of an activation energy process. Okay, which is shown here. And this is also a very, very fundamental central equation in all of electrochemistry. It's a so-called Butler-Volmer equation, which describes the characteristic, the voltage current characteristic across an interface when it is governed by charge transfer. Just think of it as an electron that has to go from an electrode into this ionically conducting medium on a species, or let's say hydrogen that has to give away an electron and become a proton. Okay, it has to go over a certain activation energy. So there is an exponential relationship. Okay, so in the beginning there is little current, but when you allow for enough voltage loss, your current is going to increase exponentially. Okay. On the other side, if you are dominated by mass transfer phenomena, you're gonna enter into a limiting current. Okay, this is just simply the physical fact that you cannot draw more current than species that you bring to your interface. Okay, you have to have enough hydrogen molecules and oxygen molecules that reach your platinum particles so that you can convert them to current. Okay, if they are somehow hindered because of diffusion, because of a bad porosity microstructure or so, then at some point you can't pull more current than the species that arrive at the interface. Okay? This is mass transfer limitation. So then you will enter into a limiting current. And of course you want to avoid all that. Okay? So you want to make these losses as low as possible. And then you find this typical characteristic, the so-called voltage current curve. I had shown you in the examples when I discussed the principle, I had always shown you for simplicity a straight line. Okay? In reality, it's a bit more complex. In reality, we have this typical S-shaped behavior, okay? Where here we are more governed by this so-called charge transfer loss, where we have an exponential relationship. And in the large current density, we have more like a cutoff. We are limited by mass transfer loss, okay? Where we start to get limited by the way how we can bring species to the interface and extract the products from them. Okay? And so then your operating point, we want to be somewhere here, okay? So, because what happens here is that we start to convert almost all of our fuel, okay? And this is a point where the voltage breaks down because we have no more driving force, okay? If I'm converting all of the fuel that arrives at my interface, there's no more reason for the oxygen to go through or for the hydrogen to go through, and my voltage breaks down, okay? That's really the essence of the EMF, of the electromotive force, of the driving force, okay? You always need some oxygen left, some hydrogen left, some fuel left at the other side, otherwise the driving force breaks down, okay? So this is why you can't reach 100% what we call fuel conversion or fuel utilization, okay? We want to push it pretty high, okay? Because this goes directly into your efficiency, of course. Okay, this I will skip. This is just another example. So eventually, my practical cell voltage is the equilibrium voltage minus the losses, the sum of the losses. Okay, ohmic losses, and over voltage loss, over potential at cathode and at anode. I give an example here with some figures. So here we come to the efficiency. Okay, so this is now the essence of the whole thing. Why is a fuel cell efficient? This is the power, electric power, output. This is the input power. The input power is the fuel heating value times its mass flow. Okay? Then we also get watts, because we want to compare watts with watts. Okay? Output watts and input watts. So my input watts is the energy content of my fuel times its mass flow rate. So what do I do here? Well, my power is current times voltage, okay? And here I use a trick. I insert my Gibbs free enthalpy, I multiply and I divide, and so I just multiply with 1. But of course I do this for a reason, because then I can rearrange this equation into, in fact, 3 ratios. Okay? I have 3 ratios here. I have a thermodynamic ratio, a thermodynamic efficiency, which is the free over the total enthalpy. Okay? And as I already mentioned, with hydrogen, we have a loss here. With methane, no. This efficiency is 1. It's a good point for methane. Then here, I have a voltage ratio. This is my effective voltage during current flow over my equilibrium voltage at 0 current. So this is actually stands for how much voltage losses I have in my fuel cells at a certain current density. Okay? Voltage efficiency, and then the last one, the third one, is the current efficiency. So this is what I explained before, this so-called fuel utilization. It says how much, which fraction of the fuel that I inject actually is converted into current. Okay? There will always be some rest fuel coming out, which of course is lost. That is a loss with respect to the efficiency. So you see, it's a multiplication of these 3 that gives me the efficiency of the fuel cell. And if this is 80% and this is 80% and this is 1, I have 64% efficiency, and this is what I reach in reality. Okay, this is why it's possible to do. So this is shown here. Okay, so this is true. Okay, we with our fuel cells there, with the ceramic fuel cells, this is what we do, and this is no theory. This is no dreaming, no painting in the sky. This is real, the real system that we sell on the market today. Right. Yeah, okay. This is going to take a little bit of time as well, but it's important to explain. Not only are they efficient fuel cells, but they're also efficient over when you change what we call the power modulation. Okay, when you go between full load and so-called part loads. Okay, so you know what full load, part load is? If you think about an engine, okay, about a turbine, any system, it has a nominal power, right? Let's say 100 kilowatts. You buy it because it gives you 100 kilowatts. And then it has a specified efficiency at that power. Okay? Now, nothing prevents you from giving less fuel to that system, to your car. This is what you do in your car. Okay? Your car, maybe, how much horsepower is 100 kilowatts? Who knows what horsepower is? How much horsepower is 100 kilowatts? I don't know. It's around 140. Okay. Horsepower is approximately 3/4 of it. Now, of course, you're not pulling 100 kilowatt of your car the whole time, right? If you're driving at 20 kilometers an hour in the city, you're using a few kilowatts. Okay? So it means you go over a wide modulation range. You just play on the amount of air and fuel that you give to your engine, right? It's the same with the fuel cell. Okay? I can have a 10 kilowatt fuel cell. It means I have to give it a certain amount of fuel and air, but I can also go down, and then I can only pull 5 kilowatt or 3 kilowatt from it. Okay? Now the interesting point of the fuel cell is that part load efficiency is higher than full load efficiency, whereas in an engine and a turbine, the part load efficiency is always lower. Okay? And the reason is explained here. So here again I've taken a simplified voltage current characteristic, which again for simplification I've made it linear. Okay? It's an approximation. And I just say, okay, I have a slope, which is half an ohm. I lose half an ohm square centimeter, which means that if I start from a volt, again I make it simple, start from a volt, and I reach 0.4 amps per square centimeter current, with half an ohm loss, I lose 200 millivolts, okay? And my operating point is 0.8 volts. So I run at 0.8 volts, 0.4 amps, and I inject an equivalent amount of fuel, which is 0.5, okay? So basically meaning that I am converting 80% of my fuel into current, right? So I have 80% fuel efficiency, current efficiency, 80% voltage efficiency, and 100% thermodynamic efficiency, supposing I'm running on natural gas, on medium, okay, where the efficiency is 1. So I have 64% efficiency, right? This is what we do. This is what we do with these cells, okay? This is our operating point. This is exactly our operating point, 0.4 amps, 0.8 volts. Okay? I can tell you in the lab we have reached 75% efficiency with these cells. This is a world record, by the way. We should have published in Nature or Science, but we have no time to do it. So now let's go to part load efficiency, okay? So, and what will I do in part load efficiency? Now I'm going to say I'm going to throttle my fuel input. I'm going to divide it by 2, okay? I'm going to inject just half the fuel. But I'm going to keep my fuel utilization, the fuel conversion, I keep it the same. I'm continue to use only 80% of my fuel into current, okay? So what happens? So I've reduced my fuel flow. I'm injecting an equivalent of only 0.25 amps. I'm producing 0.2 amps, okay? Half the current, but still 80% of it, okay? But now, since I'm at half the current, I'm also at half the voltage loss, right? So I'm not losing now 200 millivolts, but I'm losing only 100 millivolts. And this reflects directly in my efficiency. Now my voltage efficiency is not 80%, but it's 90%, okay? Hence my part load efficiency at this point now, I'm 72%, okay? And I just told you we did it, okay? The lab, we reached 75% efficiency, okay? So this is another very interesting aspect of fuel cells, the fact that you can modulate the power and that the efficiency stays high, okay? And this again, this is different from the classical combustion technology. So if you take engines, if you take turbines, if you take combined cycles, they reach certain efficiencies, but typically lower. and they reach only the highest efficiencies for very big systems. Plus we have a combustion, we have pollution. Okay? The combustion, the pollutants, the unburned hydrocarbons, the carbon monoxide, the soot, the NOx, it all comes from the flame, okay? from the combustion and from the improper mixing. Okay? In the fuel cell, on the other hand, we don't mix fuel and air. We take the electrons from our methane to give them to oxygen. Okay? We do this very efficiently already at small power, and we have no pollution. So that's the interest of the system. Here, an illustration of the part load efficiency. Okay, what this means. So let's take a gas engine 5 megawatts. Here it's running at 100% of its load. So here it is running at 5 megawatt. Okay, and then I decide to lower the fuel inlet and the air inlet in my turbine, in my engine, excuse me. And so I decide only to here 50%, so I decide only to run it at 2.5 megawatts. Well, my efficiency goes down, a few percent points, but it goes down. Okay? Same for a gas turbine, okay? Efficiency goes down. Micro turbine, efficiency goes down, part loads. Fuel cell, efficiency goes up, part loads. Simply because of the IV curve, okay? Because part load means less current, means less voltage loss, higher voltage efficiency, higher efficiency. Of course, at some point, we can't pull this through all the way here, okay? We can't say that, okay, at zero current, we have 100% efficiency. First of all, it makes no sense, okay, to produce a very, very small current. And at some point, of course, in your system, you have parasitic consumption of electricity, right? In a complete fuel cell, you have to circulate the air, you have to circulate the fuel, you need some control, so you have consumption, right? So at some point, of course, the own consumption takes over, and then your part load efficiency and very low part load is also going to drop. So,
Sorry?
yes.
Could you just go 3 slides back for the operating current? I don't really understand the percentage when you say the operating current stays constant. When you reduce the fuel flow.
Well, before here, so my operating point is 0.4 amps per square centimeter, okay, and I'm injecting an equivalent fuel flow of 0.4 amps, okay. Let's assume, I don't have now at the top of my head, and it depends of course on the size of the fuels, but let's say it's a liter per second. Let's say we inject a liter per second of fuel, okay, and we are in this condition here. And I am consuming 0.8 liters per second of this fuel. I'm converting to current. And the remaining 0.2 I recover at the outlet, okay? So I'm converting 80% of this fuel into current, right? Now we decide, instead of injecting 1 liter per second, I inject only half a liter per second. And now I'm going to convert 0.4 liter per second into current. And 0.1 is unconverted. It means my ratio, I'm still converting 80% of my fuel into current. So my fuel conversion, my fuel efficiency is not changing. Okay? It's still 80%. But what is changing is my voltage efficiency. This is what makes it different. Okay, applications, advantages, challenges. Shall I liven you up a little bit with some animations? Maybe, yeah, I will do that. I prepared some things here. We need sound. How do I get sound? Can I get sound? Huh?
The last moments in civilization, how you feeling?
That one? Work? I hope it's not gonna.
Death Valley, surviving water.
That's not work. Unless I. Well, it's a little bit a pity, but okay, I'll. I can talk to it. So you see the idea. So So this is a couple of actors, and they go to the challenge of driving through Death Valley with a fuel cell car, okay, without water. The idea is that they survive on the water that their car produces, right? Because you have hydrogen and air, and the only product, the only exhaust of your engine, your fuel cell engine is water, right? Obviously, they have made some treatment to it, and they have added some minerals because your fuel cell produces distilled water, pure water. And you know what happens if you drink pure water? You have to rush to the toilet, right? So because you always need minerals. So, but the idea is, the message is there. Okay, it's a car that allows you to survive in Death Valley. Okay, because it produces water, right? Which is not something that you would do with a regular car. You would not drink its emissions, right? Anyway, so it's a little bit a pity that we don't have the sound here. Yeah, you see, brushing their teeth and washing their face and everything. Okay. It would be nice though if we would find, because I have a few other movies, if you would find sound. Huh? Okay. Let's go back here. So you want in your lecture, you want to know how to integrate all of the technologies that you see in each module, how to integrate it into society for its application and to move to renewable energy. Well, this is an overview slide for you here. Okay, so which fuel cell for what application, where do you use it, when, and what size? Okay, so we go from small power to, let's say, medium-sized power, different applications, and these are the different fuel cells that you can use for that, okay? So it now more looks that we actually have two dominating fuel cells, okay? One is the technologies, one is the polymer electrolyte, that's really for the mobile application, cars and buses, it's running on hydrogen. We need a hydrogen society for that. And then the solid oxide, the ceramic, which is also pretty versatile and the most efficient and which we can use for small power and larger power. Not saying that the other fuel cells don't exist or don't have their relevance, it's just that they are developed on a lower level, okay? For example, PAFCs and MCFCs, there's one company making them. And it's a large company, very successful, that have installed multi-hundred megawatts of fuel cells, but there is a risk because if this one company pulls out, then it's more or less the end, okay? Polymer electrolyte, solid oxide, we have a strong activity. There's many companies involved. There is a supply chain installed, and polymer electrolytes, I'm positive we're going to see it. It's going to come. It's going to break through. And in the future, you will be driving fuel cell cars, and you will be filling your car with hydrogen. Okay, so this is this is a box. This is in fact our product. Okay, our company that we work with, Solid Power, based in Italy, in the Trentino area, in the northeast. This is what they make. Okay, we have a factory in Italy, we have a factory in Germany, and this is the product that they make. It looks like a washing machine. It's a solid oxide fuel cell that delivers you 1 to 2 kilowatts of power from natural gas. Okay, at 60% efficiency. Just recently, it has been certified at a certification company, and we are now reaching 62, even 63% efficiency. Net AC, yeah? Net AC, so that includes all the parasitic consumption. So that's a world record. And you can do it then, if it's modular, so the more power you need, you basically have to add these units, these stacks. There is one company in the US, Bloom Energy, which is very successfully doing this. You can see these boxes, these so-called Bloom boxes. You can see them standing somewhere on the road. That was 2 years ago. I was in California. where this company is based and where they are doing pretty strong. And I was just visiting, and one of the colleague professors said to me, "Oh, by the way, you see Bloom box standing there on the side? Yeah, and it's, so you see these boxes there, and it's SOFCs, hundreds of kilowatts, megawatts that are turning, that are humming quietly away, no pollution and no noise, and just turning natural gas with 60% efficiency into power." Buses. So buses is a big thing. It's going to become big. Here is it's a Siemens. It's a MAN engine manufacturing company. They're making fuel cells or building fuel cells into buses. So you see here, this is 120 kilowatt rated power, and you see at rated load 56% efficiency, hydrogen to the wheel. At 20% partial load, 68% efficiency. 68%, 2/3 of the chemical energy of your hydrogen goes to the wheel. I was 2 weeks ago, I was in Brussels on the annual review days of fuel cell and hydrogen community. And when the meeting was over, we were driven to the airport, Brussels airport, in a hydrogen bus, which is very nice, very good feeling. So here you see efficiency versus load here, okay? So you see this bus is 120 kilowatts, and you see this is the fuel cell module. This is essentially the IV curve, okay? The power current curve. Okay? This is then the whole system, the fuel cell system. As I said, in the lowest power range, it has to come down because you start to consume parasitic consumption. And then you have, after the transmission, this is then the electric motor, basically, where you have an additional loss. So final operating curve is the red one, and this compares to the green one for diesel, okay? So you see that over a wide range of the operating curve, you are 5 to 10% more efficient, okay? But especially, it's pollution, okay? Especially you have a clean bus, right? You can go and sniff at the exhaust if you want there. Nothing's going to happen to you. And China is now moving to that, okay? Because China really has an issue with pollution, and they are going to convert. They want to convert their buses to electric, okay? And their trucks. China is a country. They produce 500,000 buses a year. 500,000, okay? Diesel buses. So you imagine if you can change that to hydrogen, it's gonna make a big difference. Okay? This is a tiny fuel cell running on methanol, powering a cell phone. Okay? And this is another concept. This is then for cars. Okay. And so here the idea is again to be completely renewable. If you have photovoltaics on your house, you have an electrolyzer. You make your own hydrogen and oxygen. You tank it on board your vehicle, and you drive basically on sun power, right? Your hydrogen is sun-derived. So you have no emission over the whole chain. Oxygen is a little bit dangerous to do because it's very corrosive and explosive, so they've come away from that idea, so it's now hydrogen and air. But so there is a company in Switzerland that has done this very successfully. First in the Swatch group, under the name of Belenos, and then they moved out to Fribourg. They are actually in EPFL Fribourg, in Blue Factory, okay, where they have their testing lab, and they're building these polymer electrolyte stacks of 10 kilowatts, which they put in cars. And they're also making 100 kilowatts, which they put in trucks, and which they put in boats. Okay? And you may have heard of the consortium, this new consortium called, there's a company called H2 Energy. And it's an incentive of Co-op, of Migros, of Agrola, and a few others. Okay? So rich companies with deep pockets. Okay? Co-op is 30 billion Swiss francs chiffre d'affaires per year. And they have, they detain 1,500 filling stations across the country. Okay? The Coop, the Migrolino, and the what are they called? The little Coop shops, the station service, right? So they have the infrastructure where they could basically add hydrogen filling station to that. They also have the need because of logistics. You know, Coop has 650 trucks. 650 trucks to go from the depot to all the supermarkets and to move around food. Coop announced that in 2023 they want to be CO2 neutral. Okay? So that's 2023. That's tomorrow. Okay. So they've converted their first truck to hydrogen. Okay. From a hydro plant, so it's clean hydrogen. Okay. And this is the future. This is the future. This is how we can make a contribution to clean mobility of the future. We use PV, wind, hydro. We make clean hydrogen. And we put that in cars and in trucks, and without any pollution along the whole chain. Yes?
So do you think in the long run, fuel cells will be used more in mobility than just batteries or LEDs?
This is a big discussion that is ongoing. It's a kind of a religious war. You know, electric mobility, should it be batteries or should it be fuel cells, should it be both? I think there is space for both because batteries is for the shorter range. Okay? You know that 90% of driving is less than 50 kilometers a day, okay? Which can be easily covered with batteries, right? We only need the tank of 500 kilometers, you know, it's rare, okay? It's in 10% of the occasions. And this is why you need a range extender, okay? A fuel cell is essentially, it's called a range extender to a battery because you have an electric car. The best combination is really that, and this is what this company has done. It's called Swiss Hydrogen. They've now been taken over by a big French group, but they continue to develop. It's an electric car with a battery and with a fuel cell, okay, with a hydrogen tank. And basically, you are no longer limited by your battery in driving distance. When your battery is empty, your fuel cell takes over and recharges your battery, okay? And there's a very good combination between the two technologies because if you only rely on battery, you discharge, recharge, discharge, recharge, discharge, recharge, which is not good for the lifetime. Also, you don't have fast recharge, okay? Even though Elon Musk, he may claim what he wants, but he can recharge his Tesla in 20 minutes at best, and it doesn't do very good to the battery. But you know, 20 minutes is 20 minutes, so it means you have to put your Tesla there, you have to go and smoke, or you have to go and, you know, buy a Snickers or, you know, make some phone calls. But hydrogen, it's 2 minutes. It's open up, that's it. You know, it's like yeah. So the thing is, the trick is that you never empty your battery if you have hydrogen. You always keep the battery in a high state of charge, okay, because you recharge it. And this is much better for the lifetime. You know, one thing that you maybe also don't know about batteries is the difference between winter and summer. If they say they sell you their car, you know, your autonomy is 200 kilometers. That may be in summer, but in winter your autonomy is 100. It's a factor of 2. A cold battery is not good. So, yes.
You said that car wants to change to zero CO2.
Yeah.
Can they convert their actual truck or have by people?
No, they. I think they did. What the company did is they took. I don't remember now which truck. Yeah, but they. I believe they took the engine out and they just reconverted it. Yeah, they just reconverted it. But the other thing, of course, is to buy. I mean, you have electric trucks, and then you add a fuel cell to that. Okay. So I'm not so sure how they're going to do it, but yeah. You can reconvert.
Wouldn't this combination of batteries and fuel cell be perfect for airplanes? Even more than trucks?
I'm not so sure whether you would get the thrust. You know, airplanes you need a huge amount of thrust. Huh? So the propulsion power. And I'm not sure whether you get there for passenger airplanes, whether you would actually get that sufficient amount of power, and especially to carry it with you to drive. I think kerosene will be the last fuel that we will still keep oil for, you know, because we are totally dependent on kerosene for flying.
Because Airbus has this project, they were making a hybrid plane
Yeah,
with gas turbine,
yeah.
the battery for takeoff.
Okay, so it's with the turbine. Yeah, it's with the turbine and the battery. Yeah, that I can imagine. Yeah, but somehow you need a turbine. Okay, you need to thrust in order to be able to take off.
I may just add something, it's not the volume, one doesn't work for everything.
Sorry?
Because kerosene has a very high energy density.
Yeah, yeah, yeah.
Hydrogen doesn't have this.
Yeah, yeah. Also, yeah, also.
How safe are these systems in like case of accidents and stuff?
Yeah, this is. Je finis maintenant. Ouais. D'accord, merci. Yeah, I didn't finish quite, but you know, I mean, we are over time, so you can look at the rest of the slides. I just have some slides on the fuel issue and and on electrolysis, which would have been nice to discuss as well. But anyway, I think you get the idea. Safety is it's a paradigm. It's we have accepted the fact that we drive on a tank with 50 liters of liquid explosive, okay? Because that's what we do. And if there is a leak, if there is an accident, if it catches fire, there's nothing you can do against a gasoline or a diesel fire. If you're stuck in your car and you don't get out, I mean, you're gonna be grilled, right? And you have no chance. And with hydrogen, the tanks, first of all, they're made extremely robust. Okay? So they're composite polymer materials, which are subjected to crash tests. So they can be crushed, and they can withstand quite some shocks before they would actually rupture. Okay? In the case of rupture, hydrogen is the lightest element that there is. Okay? So it just escapes. Okay? And even if it catches fire, the speed of flame is really, really fast. They are capable of consuming the hydrogen of a complete tank within something like 20 seconds. Okay, it's just like a torch, and it just consumed in seconds. Okay, and so it's way safer. You know, it's just a paradigm. You know, it's these things, if they to drive on the road and all that, they have to be certified, they have to be homologated. And there are videos that you can YouTube and so that you can download, that you can check out, you know, about hydrogen tank testing, safety, crash tests and all that. They are quite spectacular. There is one that BMW did. You know, BMW, they are working on liquid hydrogen. Okay. And also for engines. Okay, it's not necessarily fuel cells, but they work on hydrogen engines. It's mainly for the green image. And one of the things they do, they work on liquid hydrogen, because in liquid hydrogen you can have more energy density. Now it's very inefficient because you need a lot of energy to make hydrogen liquid and to keep it liquid. Huh? It's minus 250 degrees C. So, and they made the test with this huge hydrogen tank, liquid hydrogen tank. They put it outside on a testing phase, and everybody's standing in the distance watching what's going on, and they put the fire below. Okay? They just wanted to see what it's going to do. This hydrogen tank is exposed to fire. And at the moment it burst, you know what happened? The liquid hydrogen extinguished the fire. Because it's minus 250 now. So that was quite unexpected. But, so, no, I mean, it's you know, we work with natural gas. You know, natural gas has been around for decades. Pipelines in houses. Hydrogen is just another gas. It can be dealt with. So I apologize if I'm not quite finished with everything. If I jump to the conclusion, so you see, yeah, there was a lot to say about the fuel case and about electrolysis.